Good morning, everyone, and welcome to another at-home chemistry. Today is going to be a little bit different than the past couple because I'm going to be going along with the new unit's PowerPoint along with the packet of fun. So if you want to follow along in a similar way, you can open up both of these things in your Notability so that you can best follow along. At one point, I might end up completely getting rid of the notes, but if you want to have it there so that you know what to write down over here in your packets, then feel free. Otherwise, you can just follow along, and we'll be taking looks at pictures, and we'll be on the first couple pages of your packet of fun. So first up, our new unit is called Solutions, and I'm actually going to get rid of my packet for now. So it's called Solutions. In this unit, we're going to be talking about when things mix and create a solution. Now remember, a solution is a homogeneous mixture. Let me go down here. It's a homogeneous mixture, which means it has two or more things mixed up and you cannot see the different parts with your bare eyes or with a microscope. On the other side of that, you can also have a heterogeneous mixture like sand and water or milk or dirty water, and you can see the different parts, okay? Now, solutions are homogeneous mixtures, but today we're going to talk about when something or why something forms a solution versus a heterogeneous mixture, okay? So we're going to hone in on a solution. At this point, you guys can begin writing in your packets of fun. So a solute is basically the substance that's being dissolved. If we're thinking about a solution of salt water, then the solute would be the salt. If we're thinking about sugar water, then the solute would be the sugar. The solvent is the substance that the solute dissolves into. Now, our universal solvent is water because it dissolves a lot of things. There are also other solvents, and that's on this next slide here. The different types of solvents that are out there. If it's an aqueous solution, then water's the solvent. If it's a tincture, then alcohol is your solvent. There's something called amalgam, and that's when mercury is the solvent. So mercury can dissolve things. Now, this used to be used in teeth fillings. I'm not sure that this is the case anymore. If you got a cavity, they would use mercury as a solvent, and then they would fill your cavity. And then we can also have organic solvents, and this would be like any gasoline or petroleum. So we have gasoline, benzene, toluene, and any other carbon-based solvents. Now in this unit, we're really just going to be talking about aqueous solutions. So don't worry too much on the others. If you didn't already do so, make sure that you get the definition of solvent down, which is the thing that does the dissolving, and generally it's present in a greater amount. For instance, you would have a cup full of water and then just put a little bit of salt into it. Or if you're having tea, you would just put a little bit of tea in there or just a little bit of sugar to sweeten it up. So the solute is present in a lesser amount, and your solvent is present in a greater amount. The next word that I'm going to talk about, and actually I'm going to flip over to be looking at your packet of fun now. The next word I'd like to talk about is the word solubility. Now, if I ever say the word solubility or you see it anywhere, it just means whether or not it's going to dissolve. So if something dissolves, then it is called soluble. And if something doesn't dissolve, it's called insoluble. You are going to see these words, and you will need to know what they mean and how to use them. So, for instance, sand is insoluble because it does not dissolve in water. Salt is soluble because it does dissolve in water. So be sure to know those words. All right, so next up, why do solutions even form in the first place? So it has everything to do with their intermolecular forces, which is why we had to have the last unit before this one. We had to cover intermolecular forces and how matter interacts and attracts to one another in order to understand solutions. So it says here, well, first, it's because of their intermolecular forces. When substances are mixed together, new intermolecular forces form. These are sometimes stronger than the intermolecular forces between the original compounds if they aren't mixed. And if this is the case, mixing is favorable. Another thing I want to mention is entropy. Mixtures end up having more entropy than pure substances. So because mixing is favorable, entropy is increasing. So let's talk about a little bit more closely how we can determine what is going to dissolve in what. And then I'm going to talk a little bit more about the intermolecular forces of things. So we are going to take a look at these pictures here. And I do want you to highlight this area where it says like dissolves like. When we say the word like, what we're talking about is polar compounds dissolve in polar. And you guys can be writing this down with me. And nonpolar dissolves in nonpolar. But polar does not dissolve in nonpolar. So be sure to get that down. Polar dissolves in polar. So if we have a polar compound, it will dissolve in another polar compound. And nonpolar dissolves in nonpolar, but polar does not dissolve nonpolar, and nonpolar does not dissolve polar. So if we see the separate parts of a mixture, it's safe to say that one part of that mixture is polar while the other part is nonpolar. If we mix two things together and we get a solution, and that's a homogeneous mixture, and we cannot see the different parts, it's safe to say that like dissolved like, and both the parts of the solution or all the parts of the solution are polar, or all the parts of the solution are nonpolar. So let's take a look at this image here. This is oil and water, and we have an oil layer here and a water layer. And if you guys have ever gone to an Italian restaurant, the same thing happens when they put oil, and I think it's balsamic, into the little dish in front of you, and you see it separate out, and it kind of looks like bubbles, but they're not quite bubbles. Now, what's going on here is water, and you guys should already know this, but water forms hydrogen bonds, and it is polar. Now, since it does not mix, okay, we see the oil layer on the top, and then we see the water layer on the bottom. It's safe to say that our oil layer is nonpolar. So because these are different, they are not like, they do not dissolve in one another. Let's talk a little bit more closely about why. So think about what force of attraction would be among nonpolar molecules. That would be London dispersion forces. Or I'm just going to write dispersion, actually. Which is weak, if you guys remember from the last unit. Those are weak intermolecular forces. Okay. Now, water forms hydrogen bonding, and this is very strong. So when things mix and like dissolves like, it's because one of the compounds ends up feeling an attraction toward another compound. But here, water remains more attracted to itself because it undergoes hydrogen bonding, it does not feel much attraction for the nonpolar molecule. So therefore, water continues to stick to itself and feel attraction toward itself because nothing very attractive came along. So these remain separate. Now, when you have two liquids, this is just a little extra thing. So if you guys have makeup remover, not the pads, but like liquid makeup remover, you'll actually see the liquids look like this. Go take a look at it and you'll actually see like two clear liquids separate. When you have two liquids that remain separate, it's called immiscible. Immiscible, let me highlight that here. Immiscible is when two liquids remain separate. But when you have two liquids that are mixed together, such as acetone and water, that's when they're called miscible. Sorry, I messed up those words there. So miscible means soluble, and immiscible simply means insoluble. That's if we're talking about covalent molecules, polar versus nonpolar. Okay. Next up, I'm just going to talk a little bit about ionic bonds being soluble and whether ionic bonds are soluble or not, and you should quickly know the answer to this because you already learned about ion dipole attractions. Yes, they can be soluble. Not all of them are though, okay? So it says here some ionic compounds are soluble, and it also says, but the ion dipole forces between the ions and water must be stronger than the ion-to-ion forces that hold the compound together. Okay, so the ion dipole forces must be stronger than the ion-to-ion forces. And we're going to take a look at what makes them stronger versus weaker on this image at the bottom here. Then I have here, if an ionic compound is insoluble, then the ion dipole forces between the ions and the water are weaker than the ion-to-ion forces. So the full positive and full negative would have a stronger attraction to each other than a polar water and the ion dipole forces. All right, this is one of my favorite pictures. Can't really explain why, just really love it because you can truly see how the water separates the different ions. So this is a salt crystal. We have a crystal lattice here. Now remember, NaCl is ionic. Okay, it's an ionic compound. Now you might be thinking, well, the ion-to-ion forces are always stronger than the ion dipole forces. But take a look a little bit more closely. Look how many water molecules are surrounding this ion. So you see here, or I guess recall that the solvent, which is water, is always present in a greater amount. Okay, even if you put salt on your food, you have much more food and water in that food than the actual little bits of grated salt that you put in there. So what happens is the water molecules, and you'll notice, so because you learned, I don't know what color to use, you learned in the past that the hydrogens become partially positive and then the oxygen becomes partially negative. You see here that the negative chlorine is surrounded by the positive sides, partially positive sides of water. Now what ends up happening is that it eventually separates out that ion from the rest of this crystal lattice. Okay? And then you take a look here, you have the negative sides, the partially negative sides, the negative oxygens of water are surrounding the positive sodium ion here. So what ends up happening is that it blocks it off and it separates it from the rest of the structure. Now the reason that this is a physical process is because if we were to evaporate out these water molecules, okay, they wouldn't be around anymore. If we were to evaporate them out, eventually those salt crystals, the solid, would reform because the ions would be able to feel attraction toward each other again. And that's why if you ever go to the ocean and take a little swim in the water, you end up feeling a little salty after you dry off because the water evaporated out or off of your skin, or it soaked into your skin and it left behind salt crystals. Okay, they reformed. this process of water surrounding these ions like this, and you can really see it closer in this next image, it's called hydration. It's just when you add water to something. I am going to make a separate video though. I'm just going to go over the notes on this next page, and then you can watch the next video before you do this homework. Okay. So, this page is really easy. It says here, what factors affect how fast the solute will dissolve? So I want you to think, if you put sugar in your tea, what factors are going to affect how fast it dissolves? And you should be able to think very quickly what two of them are. And one of them is stirring. Okay, so if you mix, okay, if you mix the solution, if you have an increase in your mixing, then that's going to equal an increase in your rate of dissolution, which is what dissolving. It's another word for dissolving and like speed and stuff. So it increased, and I don't know if I spelled that correctly. Sorry if I didn't. Another thing you can think about is if you make lemonade versus hot tea, the temperature makes a huge difference in rate of dissolution. So this is how fast something can dissolve. So the higher the temp, the higher the rate of dissolution. Okay, so it will dissolve faster. I think I spelled it correct that time. I was just being really messy. All right, the very last thing you might not think, you might not think of very easily. And I want you to think about why you grate your salt or your sugar before you put it into your food or your tea. So, and that's because you're making the particles smaller. So particle size makes a huge difference. And another word for this is surface area, or another way we can think about it, a surface area. So as size decreases, that equals an increase in how quickly it will dissolve. So the smaller the piece of salt, the more quickly it dissolves. And I want you to think about why. So I'm just going to draw some small pieces of salt or sugar here, however you want to think about it. And then I'm going to draw one big chunk. Okay. Now, we just talked about why something dissolves, and it's because of the intermolecular forces of that something with the solvent that it is in. Now, if you take a look, the areas where this big chunk of salt or sugar would feel attraction towards, say, water, it only has so much surface area on the outside. Okay, there are only so many water molecules that can come in and start separating it, okay, and dissolving it. Over here, each little circle, I can't zoom in on it anymore, but each little circle, those water molecules can surround every little circle. So because there's an increase in surface area, if you combine all the surface areas of all these little circles or these little bits compared to the larger whole, the water will be able to separate these little bits a lot more quickly than separating the outside here and then the outside again and then the outside again. So as the size decreases, the rate increases. Next up is what factors impact how much solute will be dissolved. So what we just talked about was the rate at which solute dissolves. Now we're talking about, amount of solute. Okay, amount of solute dissolving. Okay, so in what circumstances are we able to dissolve more? In what circumstances do things dissolve less? Okay, so first we're going to take a look at this temperature diagram. So you can see here solubility, if you take a look at the axis here at the unit, it says grams per 100 grams of water. So what this means is as you look at these numbers on the y-axis, those numbers represent grams of whatever substance that we're looking at dissolved in 100 grams of water. So that's what this unit means. You are going to see this throughout this unit. So keep that in mind. So this particular diagram is representing majority solid. The x-axis represents temperature. Okay? Temperature does impact how much can be dissolved. So what we see here is at 10 degrees, let's take a look at the red line. That represents NaNO3. So at 10 degrees, about 80 grams of NaNO3 is able to be dissolved in 100 grams of water. Oops, 100 grams of water. Now, if I was to increase that temperature, okay, if we were to increase that temperature to 60 degrees Celsius, take a look. We're able to dissolve more. We can dissolve about 110 grams into 100 grams of water. So as we increased the temperature, you have an increase in the amount that you can dissolve. But I do want you to write down that most solids increase in solubility with increase in temp. We have solids in this diagram. This one is gases. So I want you to think of gases really far apart. Their ability to be dissolved in a liquid. Now, if we increase the temperature, so here's a little fire here. You increase the temperature, maybe we change that into a reddish color. Because why not? All right, we increase the temperature there. Now, what ends up happening is those gas molecules, they speed up. They speed up so fast. They're moving around, zipping around, and eventually they escape the liquid. So it's a little bit different than the previous, where over here for solids, if we increase the temperature, like putting sugar in hot tea versus cold tea, we're able to dissolve more if we increase that temperature. Over here, if we increase the temperature of a liquid where there's gases dissolved, we increase the temperature of that liquid, you see that less is able to be dissolved. And that's because they're moving around so fast that eventually they escape the liquid. Okay? So over here you can say the increase in temp of a gas dissolved in a liquid, you end up having a decrease in solubility. Or an amount, okay, of solubility. Again, it's because at high temperatures, those gases that are dissolved in the liquid, at high temperatures, those gases are just going to evaporate out. Okay, they just evaporate out and they no longer are able to be dissolved. All right. The last thing we're going to talk about is how pressure affects solubility. So here, I want you to think of well, actually, I really like this image. We're going to take a look at this image. I want you to think of opening a can of pop, okay? Now, first off, or a bottle of pop, okay? You hear a little tss noise, okay? And eventually, if you were to leave that can of pop open, or if you pour it into a glass and you want to save it for later because, you know, maybe you had to go somewhere and you want to save it for later, you put that can of pop in the fridge, and then maybe a day later you come back to it and you taste it, and all of a sudden it tastes awful. It's just flat. So what ends up happening is when you first hear that sound, that is causing pressure that was applied in order to get that CO2 into, or the carbonation, it's CO2 dissolved into the liquid that it's in order to get that gas in there, those bubbles, it ends up, you have to pressurize that can, okay? And what that does is that the pressure from the outside ends up pushing the gas molecules above it into the liquid. Okay, so if you increase the pressure of a gas above a liquid, then you increase the solubility. Okay, if you decrease the pressure, this would be like opening a can of pop. Or if you're from any other state, soda. But we're in Ohio, so pop. But if you open it, that releases the pressure above that solution, and therefore eventually those gas molecules leave the little can of pop, and then it gets flat and it tastes gross. Well, maybe it tastes just the same. It's just we don't enjoy it as much because we don't get those little bubbles on that bubble sensation. Okay, but that's what's going on. All right, so let me see if I missed any notes. I think it was just if you increase the pressure, it increases the solubility. So I guess you can write that down. So if we increase P, that increases solubility of gas. Alrighty. And then you can see the little direct and indirect relationships at the bottom of your page there. Alrighty, I'm sorry that this video was long. You guys did great. I do want you to watch the next video before working on this practice, because you will not be able to determine these whatsoever and with in a proficient way unless you watch this video, because this little table is not going to make much sense unless I explain it to you. All right. So next up, just watch that video and then you can work on this practice for homework. Hope you guys have a great day.